Hello, my name is Niklas Sandstro, and I recently completed my PhD studies at the Department of Micro and Nanosystems at KTH, Royal Institute of Technology in Stockholm, Sweden. In this video, I will give a brief introduction to my thesis, which is titled Integrating Biosensors for Air Monitoring and Breath-Based Diagnostics. The air that we breathe is full of airborne particles. Some of these particles can be airborne pathogens that are infectious and can cause diseases. Two examples which have been targeted in this work are influenza and norovirus. These two pathogens are easily transmitted and can cause disease outbreaks with severe results. Therefore, it is important to, at an early stage, reduce or prevent such outbreaks. In order to do so, we need to be able to rapidly detect these pathogens in ambient air or, for diagnostic purposes, in exhaled breath of infected patients. However, with existing technology, this is not possible, particularly not out in the field or at point of care close to patients. My work was focused on developing and integrating new technology for the rapid detection of such airborne particles. This included the use of labs on a chip and biosensors, which are miniaturized devices that enable a rapid and sensitive detection of specific target analytes. The biosensors are integrated with the lab-on-a-chip devices and combined with an efficient air sampling technique to enable a rapid detection of airborne pathogens. Now, let's look closer at the different parts of the work, starting with the fabrication of lab-on-a-chip devices. We have developed a new manufacturing technique for Osteoplast thermosetting polymers based on reaction injection molding. With this technique, that we call Osteoplast RIM, we can quickly prototype thermoplastic-like parts that are similar to the ones manufactured in industry. In addition, we can easily bond the parts together to generate a complete device by putting the parts in direct contact and perform a covalent bonding. The method features high replication fidelity, and the devices feature low residual stress, high transparency, and a native hydrophilicity. Now let's continue with looking at how we can integrate the lab-on-a-chip devices with biosensors. We explored 3 different integration approaches using different materials, including standard thermoplastic polymers and osteoplast polymers. A strong focus was on how to reduce the design and integration complexity compared to state-of-the-art biosensor devices to enable disposable use in field applications. Here are 2 fabricated devices that feature a minimal amount of parts and a very straightforward type of integration. Lastly, let's take a look at how we can capture airborne particles to these devices. To enable liquid-based sensing of airborne particles in lab-on-a-chip devices, we need to be able to transfer the particles from air to liquid. For that, we have developed a perforated diaphragm that is used for air-liquid interfacing. By using surface tension effects, the microscale pores of the diaphragm, which are seen in the image, can hold the liquid meniscus in a fixed position and thereby provide a robust air-liquid interface suitable for field applications. We then use ionization by corona discharge and electrostatic precipitation to accelerate airborne particles directly to the air-liquid interface of the device, where the particles absorb into the liquid. Thereafter, the particles are available for subsequent and rapid detection by the biosensor. With this sampling technique, we show a sampling efficiency that is comparable to state-of-the-art techniques, but with a much higher up concentration of the sample. This potentially allows for a faster and more sensitive detection. With this, I would like to conclude this short introduction to my thesis. And if you would like to know more about the methods we used or the results that we achieved, feel free to contact me. Visit my KTH profile page where you can find links to the thesis and publications, or visit the website of the Micro and Nanosystems department. Thank you.